So this would be the next topic that we'll talk about. So what exactly is memory management and what is involved? Now, as you realize right from the start, I have been reminding you about the fact that mobile devices have significantly lower amount of resources, in particular even memory, internal memory available within these devices. So obviously you cannot write huge programs that take up a lot of space on the memory. So there is a constraint on the memory. Furthermore, most of these devices do not implement virtual memory. So you don't have the aspect of infinite amount of space. Like when you studied virtual memory in operating systems course, you were told that the virtual memory approach allows the programmers to write programs without having to consider the actual size of the physical memory available within the device. But virtual memory adds overhead to the operation of the devices. It consumes additional amount because, as you recall, if you need to access any memory location, and if you're using virtual memory, whether it is paging or segmentation, if you remember from your operating systems course, or if you have taken the architecture course 4611, you would have learned about the fact that the CPU issues a virtual address, and this virtual address will have to be translated from virtual address to physical address by the memory management unit. And then after that, during this translation, you have to look up the page table where information about exactly where the page is mapped into the memory is stored. So it might actually, a single memory access to fetch any data from memory might involve actually multiple accesses to memory just to be able to fetch the data. That kind of overhead is too much for small devices like mobile phones and so on. So very often, and embedded systems in general. So very often, we don't make use of virtual memory in these embedded devices. Instead, all the required memory for a program has to be taken from the physical memory, or in other words, the entire program resides in physical memory and it can use only the space that is available in the physical memory. Now, this also means that when you write programs, you need to keep certain things in mind about the way you write programs. So today, I will sort of highlight a few of those things that you need to keep in mind when you write programs. It may be just as simple as restructuring your code to make less use of memory. So that is the whole philosophy behind this particular section. Okay? So first and foremost, obviously, you're writing programs in a high-level language. Like in case of Android, you're writing it in Java. So when you write programs in Java, the data that you use within your programs are declared in some form. Now, you declare things like, for example, in terms of integers, floating point numbers, then characters, strings, arrays of strings, characters, arrays of integers, and so on. Okay? These are all different kinds of variables that you use when you write programs. So when you write a high-level language program, you can classify the data into two types, primitive data types. These are data types that are directly supported by within the application. Things like, for example, integers, characters, and floating point numbers, and so on. These are primitive. These are supported by the language itself within which you write these programs. Obviously, you need to make the connection about the fact that when you declare these variables within the program, they have to be mapped into some location in the physical memory of the device. These data, like whatever that you declare within your objects, within your functions, and within your methods, and so on, they are all mapped somewhere in physical memory. Depending on the kind of data type and where you declare the data, where these things reside in the physical memory will be determined. So primitive types are things that are directly supported within the language. And then you have reference types or object types. These are the bigger structures that you create in order to facilitate writing your programs. In this case, the reference, or if you talk in terms of C, C++, the pointers, these point to the location in memory where the actual data type is stored. And typically, those objects are complex combination of primitive data types. And you create objects with a specific purpose in mind. Obviously, when you declare objects being instances of classes, you have a certain expectation when you create those objects, right? You have a certain reason why you create those objects. So they are more complex, and the way you access them is through references. Yeah. You have a reference, and then from that you are able to access the individual components of the object. Now let's look at some of the primitive data types that are available in Java. And you can extend this to any other programming language in general. I'm just using Java as an example, but you can extend it to other programming languages. Typically, most programming languages will support many different kinds of data types. This is the list that is supported in Java, including byte, short, int, long, all these being integer variables of different sizes, all the way ranging from 8 to 32 or even 64-bit integers. Then you have float and double. You all are familiar with this. Character, and then Boolean variables sometimes. In Java, Boolean variables are also supported. So these are primitive data types. They store a single value. Okay? And obviously, they need to be mapped somewhere in physical memory. And in addition, whenever you declare a variable, the variable comes with certain properties in mind. Okay? You have the type of the variable. Now these are what we call as the attributes of the variable, and these attributes determine how and when the variable gets created, how long will it exist, when will the variable disappear, and so on. So the first attribute is the type of the variable, the name of the variable. Typically, every variable that you use, you have to declare a unique name so that you can refer to the variable. The value, obviously stored, value of the variable stored within where the variable is mapped. The address of the variable, the location in physical memory where the variable exists. Scope. If you have taken programming languages course, you would have been taught about scope and lifetime of variables somewhere in programming languages course. If not, scope basically tells you the region within which the variable is valid and where it disappears. Now, depending on how you declare variables, the scope will be correspondingly determined. Now, obviously, when you use variables, you want to minimize the scope of the variable, because the smaller the region within the program that a variable is active, the lesser the amount of memory that you use. As an example, when you declare variables inside a method, local variables inside a method, how long do those variables exist when you declare local variables inside a method? Any method. When you declare them inside a method, the variables come into existence only when the method starts executing. That is when the method is called. And these variables get created on the execution stack. And then the moment the method exits, those variables disappear automatically. Which means that the duration for which these variables are active is limited to the amount of time that that method executes. Obviously, that also minimizes the amount of memory that you're going to use. So, one important aspect that you can take away is, if you can declare as many methods as local inside a as many variables as local inside a method and get away with it, try and do that, because that will reduce the amount of memory that you're going to use in your program. Okay, that's the first important point that you need to keep in mind also. So the scope of a variable is the block of code within which the variable is accessible. Once you exit the block of code, the variables become inaccessible anymore. Now, when you declare Java objects, obviously when you declare Java classes, you declare variables right at the top, right? You say public int, and then you declare variables there. When do those variables get created? Those variables become active when an object of that class type gets created, and then those variables will exist until that object disappears. Okay? But if you declare variables inside a method of that class, then those variables get created only when that method starts executing, and then finish when the method is exited. So that's one thing that you can very effectively use to control the amount of memory that you are going to use within your program. So the access to a variable is minimized when the variable is declared an innermost scope that is required for the variable. Keep that in mind when you declare variables. Like, for example, a variable declared like this, like int b. That is a local variable inside a method. And this variable will be in existence only when this method is executed. So the scope is only within this block of code. Once the block of code exits, b is no longer available. So the variable b will consume memory only between the time the method enters until the time the method exits. But if you declare a variable like this in a class, that variable gets created for every instance of that object, and that variable will be in existence for the entire duration of that object, the entire lifetime of that object. Okay, from the moment the object gets created until the moment the object exits. So obviously, anything that you declare up here will have much larger lifetime than those that you declare inside. So that's one important point to keep in mind. So what exactly do we mean by lifetime? Variables that you use within your program get created at some point in time. When do they get created? Depending on where you declare those variables, they get created at different times. A variable that is a class variable or a instance variable declared right at the top gets created when an object of that type gets created, and then will be in existence until the object is exited. Similarly, a variable that is inside a method gets created when the method is entered, and it gets destroyed when the method is exited. Once you create a variable, obviously you will initialize that variable somewhere. There is no point in declaring variables that you are not going to use. Okay? That's another thing that you should look for within your programs. If you are declaring variables that you are not using anywhere, might as well delete those variables. Don't use them. And fortunately with Eclipse, it points out, you have all seen those yellow triangle warnings that come up in Eclipse, right? That indicates if you declare something and you're not using it, it will indicate that you're unnecessarily declaring the variable. That's something to keep in mind. So the variable from the point of creation to the point of destruction is the lifetime of the variable. Okay? Now, depending on how the variable, how memory gets allocated to the variable, the creation and destruction of the variable is also controlled. What does this mean? Obviously, you have seen situations where you dynamically create variables. Those are dynamic variables. If you have taken a C or C++ course before, you would see that you can create things by calling the new and destroy them by giving them up at some point in time. Okay? In Java, also similarly for objects, for example, you create them when you read. So in Java, you declare classes. What is a class? A class is a collection of data which are stored in named fields. These are the variables that are available within the class, and a bunch of code which is organized into methods that operate on the data. So that's how you declare a Java object. Java class. And an object is an instance of the class. Okay? When you create Java objects, the members that you declare in a class can be of 4 types. Members are either variables and methods that you declare. You can have class fields in Java. Class fields meaning these are variables that are declared only once for the whole class. They are not recreated for each instance of the class. Each object doesn't have to store them. So these are class fields. And then you have class methods. Class methods are those that operate only on class fields. Class methods should not be touching any instance fields. What exactly are instance fields? Instance fields are those variables that you declare which take on values for each instance of the object. I'm pretty sure I'm repeating things that you have seen before, so I'm not stressing it too much, but I'm just reminding you about these things that you might have seen, whether you have taken a Java course or whether you have taken a C or C++ course, you might have been reminded about these things. In Java, we specifically use those terms. And then you have instance methods. If you're operating on any instance variables, the methods automatically become instance methods because they are operating on instance fields. Class methods cannot access instance. So this is how Java objects and classes are dealt with. Now, when you declare variables within Java, where exactly do they go? If you declare local variables inside a method, they go obviously onto the stack, execution stack. They are allocated when the method is invoked, and then they are deallocated when the method returns. That's a very good way of controlling the amount of memory that you access. Keep variables as local variables as far as possible. But one thing that you need to remember is that if you declare something as local variables, don't try to return a reference to those variables. Okay? Because if you return a reference to those variables, they will no longer be valid once the method exits. This is an important point to keep in mind. Because this particular point will often cause bugs within your program that you don't realize until suddenly at one point it dawns on you that you are trying to return a reference to a local variable. So keep this point in mind. I stress this point specifically because you might encounter that particular issue. Other data types, they usually live on the heap. Those data types that live on the heap are explicitly allocated and explicitly managed by the runtime. So you allocate memory by using the new constructor, new way of creating. You have seen this very often used in all the programs that you've seen. Whenever you need to create a new instance of an object, you say new and then give the object name correspondingly. So this basically results in those objects being created on the heap. Okay? They are created on the heap. But in Java, you don't need to explicitly deallocate. How do you do this in C++? C++ also has the new operator, right? In C, you use something called malloc. Have you heard of malloc? M-A-L-L-O-C. If you're writing programs in C, you will use malloc. In C++, it's called new. But remember, in C and C++, you have to explicitly release the memory by calling delete in case of C++, or free in case of C, and then you need to explicitly release them. In Java, you don't have to do it because Java has built in something called garbage collection, which I will briefly refer to a little bit later. And that's the reason why Java uses what we call as automatic memory management, and so dynamic memory management is used for objects. If you're writing programs in C or C++, you need to pay close attention to this. Now, those of you who write programs in Objective-C for iOS, you would notice that you need to specify some of these allocations and deallocations explicitly. Something called auto-release pools and things like that. If you have written any Objective-C programs for iOS, you would realize that these things are explicitly used there. Keep that in mind. In Java, that is not needed. And fortunately, since Android programs are written in Java, you don't deal with them. But they come with a little bit of issues that I'm going to talk about a little bit later. So that's one thing that you need to keep in mind. So you saw this term, dynamic memory, being used in the previous slide. What exactly is dynamic memory? How do you make use of it? Dynamic memory management means that the memory required by your program in the form of objects and so on is dynamically allocated to the program during the runtime of the program. Now, in C and C++, for example, you have something called global variables. You're all familiar with global variables and static variables that you declare in C and C++. When you declare something as global variables and static variables, they get created as soon as the program starts running. And then they will remain for the entire duration of the program's execution. In Java, you cannot declare global variables. Have you ever tried to declare global variables in Java? People who have written Java programs, you realize that you can't do it because there is no concept of global variables in Java. Everything has to be inside an object, right? So if you needed to do something like global variables, that is, variables that have to be shared across many classes, that can be accessed from many classes, what is the alternative in Java? The only alternative approach in Java is to declare them as singleton classes. Okay, have you heard of singleton classes? Well, if you haven't, when you look at some of the lab exercises, I have created a couple of singleton classes in the lab exercises just to illustrate the point. Singleton classes are where you enclose what would be global variables, what can be easily declared as global variables in C and C++. In Java, you enclose them inside a singleton class and then provide methods to access those variables. That kind of construction is very robust way of declaring things, but it automatically makes global variables impossible in Java. Okay? So everything has to be created specifically for the program while it is running. So creation or the allocation of memory is done from the heap. Heap is nothing but a bunch of a chunk of memory that is given to the runtime system, and then whenever you need a portion of the memory, you go and ask. How do you ask the heap for some memory? You use the new operator. You go and ask the heap manager saying, look, I need to create an object. This is the object. This is the class whose instance that I'm trying to create. So you specify to the heap manager, and the heap manager will allocate the memory to hold your object. Okay? Now, so the heap manager handles the allocation and deallocation of memory. Okay? And again, how the heap manager does its work and so on is again a very complex thing that you need to worry about. To give you an example, one way a heap manager can work is that the heap manager can simply take the amount of memory and then divide it into fixed size blocks. Okay? That's the easiest way for the heap manager to work, fixed size blocks. And then so when you ask for memory, saying I am trying to create this object, this object is an instance of this class, and then you tell the heap manager. Then what the heap manager does is it takes a few blocks and then allocates to you. How many blocks? that depends upon the size of the object that you're creating. If your object occupies, for example, 70 bytes, obviously the heap manager manages the memory in terms of fixed size blocks. Say, for example, 16 or 32 byte blocks, and then your object requires 70 bytes. Obviously, you cannot give exactly 70 bytes to that object, because you can only give it in blocks of 16 bytes or 32 bytes. So what you do is you find the nearest upper bound for that, which will be a multiple of the block size, and then allocate to it. So if you want 72, for example, if you're using a 16 byte block, then the nearest upper bound for 70 is 80 bytes, right? 16 times 5, 80 bytes. So you give 5 blocks, but then when you give 5 blocks, the object actually occupies only 70 bytes out of those 80 bytes. The remaining 10 bytes go waste. What do we call this? The concept is very similar to what you had in paging, fragmentation. That amount of those 10 bytes that get allocated will not get used, but unfortunately you have to bear with that headache. So a fragmentation problem arises. If you use larger block size, then if you need 70, the closest that you can allocate is 96 bytes, 32 times 3. But if you allocate 96 bytes, 26 bytes are going to be wasted. See, this is one of the things that you notice about the block size and the relationship to fragmentation. If you have a larger block size, you will have more wastage due to fragmentation. Again, same concept that you saw in paging is the same, exactly the same concept. Remember that if you needed a certain amount of memory, you always have to allocate in multiple pages. Same thing here. Okay? Now, but a larger block size will make heap management more convenient, because the heap manager needs to keep track of all the status of all the blocks. It needs to keep track of which blocks are allocated, which blocks are free, where are the chunks of free space, and so on. Okay? So all this means that the heap manager needs to store sufficient management data in order to manage the allocation of memory. So that's one thing that you need to keep in mind. Smaller block size, more amount of data needs to be stored for heap management. So this part will be larger for heap management. Okay? So this is one thing. So fragmentation. Let me just quickly remind you of what fragmentation is from your earlier courses, say, from your operating systems course, for example. Suppose you have a situation in memory like this. The red blocks are all allocated, and then those marked in blue are all unallocated blocks, unallocated memory chunks, and the size of those chunks. Suppose you need a memory allocation of about 500 bytes. When you look at this picture, obviously you realize that although the sum total of the available space is greater than 500 bytes, no single block is large enough to accommodate those 500 bytes of memory requirement. Okay? So the allocation will fail if you do not do anything. Now, what is one way of dealing with this allocation, dealing with this problem? One way that memory allocation, the heap management deals with it, is to do compaction. You have heard about compaction in case of segmentation, operating systems course. What exactly is compaction? What you do is you try to move all the allocated blocks to one side and then coalesce. That's the exact word, coalesce, or in simple terms, combine all the free blocks to make one large free block. But if you need to do compaction, compaction takes time, because you need to be able to move these blocks from their current locations to the new location. And while this movement is going on, all the work on the computer has to be stopped. All real work has to be stopped for this movement to be completed before the programs can resume executing. So compaction takes overhead. Okay, so that's something that you need to keep in mind. But the advantage of dealing with dynamic memory is that the total amount of memory required for your program can be reduced. Because with dynamic memory, you are creating the objects only when you need them. Okay? And those objects will be in existence within your program only as long as you need them. And the moment you don't need those objects, you can release them. Which means that your memory consumption can be more closely managed. So you can reduce. If you say, no, I'm going to allocate all the memory that my program needs right at the beginning, you can do that. But only thing is it becomes a problem afterwards, because you will be allocating so much of memory, and then most of the time you might not be using most of that memory for anything. Okay? So dynamic memory management is definitely useful to control the amount of memory that you use with your program. That's one important thing to keep in mind. Fortunately, in Java, you are forced to do it because you need to declare objects and then make use of them. But even within objects, you can try and reduce the amount of memory that is consumed. Okay? But the disadvantage of dynamic memory is that this is all under the control of the programmer. Programmer has explicit control of when they create and when they release these objects, which means that if you do not do it carefully, it might result in something called a memory leak. If you keep allocating memory for your program, if your program keeps running and running and running and running, and it just keeps allocating memory slowly without releasing the memory when it doesn't need, what happens is that the total amount of memory that your program occupies keeps growing. Eventually, your system will run out of memory. In case of Android, if your system runs out of memory, what does Android do? Remember from the very first chapter, very first section in Android? If the memory runs out, it kills. It just destroys some tasks or some processes that are currently not active. Remember that Android can kill in order to reclaim memory. Again, if you kill, obviously you are wasting some resources, because again, if you need that again, you need to recreate the whole thing. So try not to give the Android framework the opportunity to kill your process. You can cooperate with the framework by reducing the amount of memory you use, and if everybody does that, then we can all happily live together on the same Android device. Okay? So that's one thing that you need to keep in mind. Now, memory leaks, as I told you, is a source of big headaches for programmers. Anybody who does any kind of programming always has to watch out for memory leak. Okay? Memory leak detection in program is big business. Go to Google and type memory leak. Look at the number of results that you will get. It will run into millions. There are people whose main job is to create tools that help you to track your memory usage of your program. And the primary purpose, reduce the amount of memory that you use within your program. Okay? Now, memory leaks are a serious problem in small devices like mobile phones and so on. In desktops, as you will notice, memory leak is a problem, definitely a problem, but there are ways that you can get around it to an extent. What exactly is a memory leak? When your program is running, as I mentioned earlier, your program will keep allocating memory from the heap. As more and more memory gets allocated to your program, the amount of memory occupied by your program keeps increasing. Okay? If your program keeps continuously running, its memory usage will keep growing continuously. Eventually, obviously, your system will run out of memory. Okay? In case of desktop computers, or rather standard computers, you can prolong the time that you don't have to deal with the problem because of the existence of virtual memory. Because the whole concept of virtual memory is to give your programs the illusion as if it has infinite amount of memory, as if your computer has infinite amount of memory. So memory leaks are a bit more easy to deal with. But in small devices, unfortunately, you don't have, most of the time, you don't have virtual memory. So physical memory becomes a limitation. If you keep using memory continuously, eventually this device or system will run out of memory. And then that's where it starts killing processes, as in case of Android. Okay? So memory leak is always a problem. Okay? Now, with desktop computers, or rather computers in general, when I say desktop computers, just assume that I'm meaning computers, standard PCs and computers in general. What happens? Your behavior with general computers is different from the way you use mobile devices and other devices. Why? Let me ask you a simple question. How often do you reboot your computer? How often do you turn off your computer and restart your computer? Once a day? Once in 2 days? Who keeps their computer running continuously without shutting down? Nobody, right? Oh, you do? Throughout, how many days do you run it? About a month? Don't you notice that your computer keeps getting slowed down as time progresses? That's the problem. It's better to restart your computer regularly. Because what happens is when you restart your computer, if programs are consumed memory, if you restart your computer, your whole memory is cleaned out, right? And you're starting afresh. And then you will restart those programs, and then they'll start consuming memory over and over and over again. After a few days, they would have consumed so much of memory. But then if the moment you restart, it's all back to square one. Right? How often do you turn off your mobile phones? How often do you turn off your mobile phones? Some people say, hey, when I go to bed at night, I turn off my mobile phone. But most of us don't, right? We keep our mobile phones on for months at a time. Right? Because you are afraid that if you turn off your mobile phone, you're going to lose the important call that is going to come from somebody who will offer the most wonderful job in the world. Right? So you don't want to turn off your mobile phone. You will turn off your laptops. You will turn off your computers. You will never turn off your mobile phones. Mobile phones keep running for months at a time. And added to the fact that mobile phones have physical limitations on the amount of memory that they have. So memory leaks become an even bigger headache for mobile phones. In general, when you talk about embedded systems, again, one example that I gave you of embedded systems are computers that you put on board of a spacecraft that you send for probing into outer space. When you launch the spacecraft, you're obviously not going to reboot the spacecraft, right? It's going to keep running forever. So there is no scope for you to clean out the memory and then restart. So you need to be very conservative in the way you manage memory. So let me give you a simple example of how memory can leak within your program. This particular code is looking more like a C or C++ code. In Java, you would realize that this can be worked around a bit more easily, as I will explain later. But let me use C++ or C as an example to illustrate how memory leaks can happen. Look at this simple function. Okay? In this function, what are we doing? We are declaring some local variables, and then we have declared a pointer here, and then right within this for loop, we are allocating memory for an object. Okay? Where is this stored? This is on the heap. Every time you go through this for loop, you are allocating space for about 10 integers out of the heap. And every time you're creating them, and then you're initializing them, and then you're losing the pointer to that memory location that you have allocated. How many of you have encountered pointer bugs in your program that gave you sleepless nights? Right? Dynamic memory is one of those hard things to deal with unless you know what you're doing. This is a classic case of a newbie programmer doing the wrong thing. Even worse, the moment you exit the function, the pointer to the last integer that you allocated from the heap is completely lost. So all the memory that you allocated inside the function will not be accessible anymore, but they will be allocated on the heap the moment you exit from the function. All the memory is gone from the heap. You can't use that memory anymore. You have lost the pointers to the memory. It's all gone. If you repeatedly keep calling this function, every time you call this function, it's going to take away some portion of the heap. Eventually, you will run out of space. So this is an example, just one example of a memory leak that can happen. Okay? That's why we say always make sure you handle your pointers carefully. Okay? Very often we lose track of our pointers if you do the wrong things. Okay? So typical causes of memory leaks within programs. Sometimes, for example, you are passing messages between two different processes or two different threads within a process. What happens? In one thread, you allocate some memory, some buffer space from the heap with a pointer to it. Obviously, messages cannot be held in pre-declared integers. You always allocate some memory from the heap. You have an object which represents the message. You allocate memory from the heap and then pass the object to the other thread. Now, expecting that the other thread, after it reads out the information from that message, would release the space. If that other thread forgets to release the space, you have a memory leak. Sometimes you may be moving pointers around without releasing the memory. How many of you have implemented linked lists using pointers and then lost track of elements of the linked list somewhere in your code? Right? You know, especially with doubly linked lists, when you delete an item from the doubly linked list, you need to reassign the pointers appropriately. And I'm pretty sure you have had cases where you lost track of your pointers and then ended up with your code crashing right an hour before the deadline. And then you spent all your time trying to figure out where it happens. Dynamic memory is a big bear. It comes to bite you at the wrong times if you don't know how to deal with it. Okay? The third one is if you use a locally declared pointer inside a function to point to memory and forgetting to release it before exiting the function. This case is the example that I just showed you earlier. You were declaring a pointer which was a local variable, but you realized that the moment you exit the function, the local variable is gone. The pointer is gone. But the memory remains allocated. So that's the other problem. Sometimes you may be using software from some other people, right? very often you don't write your own complete code, right? If you have libraries that other people have written, you make use of them in your code. If other people write libraries, they may be passing information back to you in the form of buffers, which obviously after you read in the information, you have to release those buffers properly. You may not do it appropriately. All these cause problems of memory leaks. Okay? Now, how do you know whether your program is leaking memory? I will show you one particular tool that you can use in Android in order to keep track of how memory is being used by your program, called Allocation Tracker. It basically keeps track of when you allocate and deallocate memory, dynamic memory within your program. If your allocation tracker indicates that your memory is doing this, it will show it as a graph. If your memory is continuously going up and up and up and up, then you know something is leaking memory. Okay? So that's one thing. The other headache that you will notice is something called dangling pointers. Dangling pointers is yet another source of headache for programmers. Suppose you have an object for which you have multiple pointers pointing to that object. You do that very frequently, right? Take the example of linked lists. In case of linked list, you always have a head pointer, you always have a tail pointer, and you have a back pointer from one of the elements of the linked list. Both of these are pointing to the same memory that is holding the item of the linked list. You release the memory using one of the pointers without properly reassigning the other pointer. The other pointer is left there, pointing to a memory location that is not valid anymore. That is what we call as a dangling pointer. This problem occurs very frequently in C and C++. Dangling pointers. Here is an example of a dangling pointer. I mean, this is a contrived example. Obviously, you don't write code like this, but I just wanted to show you how you might end up with a dangling pointer. So here, for example, you have allocated some memory to be pointed by this particular pointer, and then you somewhere initialized another pointer to point to the same previous pointer. So both B and A are pointing to the same allocated object on the heap. But suppose somewhere down in the code, again, these three are not necessarily consecutive statements in your program, but they may be at three different locations within your program. But I just brought them together to show you how this problem occurs. So without realizing, you might have deallocated the memory pointed to by one of the pointers without properly. If you do this, the immediate next thing that you should do is A is equal to B is equal to null, so that you wipe out both the pointers completely. Set them to null. If you don't do that, we often are lazy and we forget to do that, right? Then you are left with the dangling pointer. At this point, B is still pointing to an address in the memory where this object was supposed to be existing, but that object is not valid anymore because you have freed up that object or freed up the memory allocated to the object. So this will leave you with a dangling pointer. Now, both of these will come back to again bite you some point in time. This is one more example of where memory leak occurs. One more little example where you might reassign a pointer to the location, but then forget to release that. Okay. Symptoms. Now, if your program has bugs due to pointers, what will your program do? See, this is where you spend your C+ nights. First, the program starts to crash in a well-tested function in the library. How many of you ever use debuggers when you wrote programs? Whether you use Visual Studio or Eclipse or anything. How many of you ever use debugging within your programs? Things like, for example, setting up break statements and then trying to trace how the instructions that are getting executed. And then if your program has pointer bugs, it will point to a location where you don't see any problem at all, very often. And that's where your C+ nights were spent. It shows you locations where no problem actually should be existing. This could happen because you might have a pointer that has become corrupted inside some code somewhere, and you don't realize it, but unfortunately it causes a crash somewhere else within your program. Because somewhere else you were trying to use that pointer to access the memory location, and unfortunately that became null somewhere, and then you have what is called null pointer exception, jump. Have you had Java null pointer exceptions with your Java programs? There's your source. This is even more headache. Sometimes the program works perfectly fine, but then when you bring the program to show for demo in front of me, the program starts misbehaving in the worst possible way. Right? This has happened to you. I'm pretty sure this has happened to you. This has happened to me too. Right? I tell somebody that I implemented the solution to the program, and then I go to demonstrate it and it crashes right in front of them. And then I'm left with a sorry face. This is another source of the program. Uninitialized variable pointers, which you will be accessing in memory, causing problems. So next time when Eclipse exits, when your program crashes, and then you see a Java null pointer exception within your program, go back and look where it is and try and figure out where the problem could be. Okay? Now, fortunately in Java, you have the help of something called garbage collection, which we will talk about on Wednesday of next week. All right?